This short video briefly goes over some resources that you can consult to prepare your tropical cyclone forecast during lab periods. We'll look at a few different types of models, performances of models, and some online resources you might find useful when forecasting. Numerical models are either dynamical, meaning that they integrate physical equations in 3 dimensions through time to simulate a future state of the atmosphere, or statistical, meaning that they make empirically based predictions based on past outcomes or persistence. Statistical models are no longer used for track forecasts because dynamical models have superior performance. However, they are still one important resource for intensity prediction. The table displayed currently shows several dynamical models used by the National Hurricane Center. Many of the models are global models, meaning that they model the atmosphere over the entire world. Horizontal grid spacing and the number of vertical levels determine the size of a discrete grid box in a model domain. The data assimilation system and cumulus parameterization are also listed for each model. Most models have new output available every 6 hours, although output from the higher resolution ECMWF is only available every 12 hours, and only limited output fields are available to the public. 2 non-global models are shown. They are HWRF and the Navy COAMPS models. They are mesoscale models that run at high resolution and use global model fields as forcing at the boundaries. 2 types of ensembles are listed on this slide. Some are consensus ensembles, meaning that they simply take the average or weighted average track or intensity of several dynamic models to create a refined prediction. Global model ensembles are made of several runs of the same model initialized with different perturbations to the atmospheric state, such as the 3 in the first 3 rows here. Their purpose is to provide a sense of the uncertainty in a model track or intensity forecast that is based on the uncertainty in the imperfect time-zero model analysis. This reduces forecasters' dependence on a single deterministic model that may or may not be correct. They capture a range of potential solutions of the future state of the atmosphere. That range is also referred to as model spread. In lab, we will be able to use global model ensembles output from GEFS, the GFS ensemble system, MOGREPS, the UK Met Office model ensemble system, and the ensemble prediction system in ECMWF. The U.S. Navy's mesoscale model, COAMPS, also produces an ensemble of solutions not shown here, but it is typically overspread, meaning that it expresses too much uncertainty. Statistical models are no longer used for track forecasting. However, one, CLIPER 5, which is based on climatology and persistence, is useful as a baseline for assessing the performance of dynamical models. Some other statistical models are used to assess wind radii and intensity. The errors of statistical models at intensity forecast are still, even in 2020, comparable to errors of complicated dynamical models, even the ones like HWRF that are run on small scales. You may find yourself using SHIPS or D-SHIPS in your forecast in this class. D-SHIPS is essentially SHIPS, but includes a decay component for tropical cyclones moving over land. These models produce output every 6 hours. The next few slides characterize track and intensity errors for North Atlantic and East Pacific tropical cyclones and compare them to official forecast errors from the National Hurricane Center. Track errors here are shown in nautical miles. Bolded values indicate models that perform better than NHC at the time represented by that column. Ensemble systems like the FSSE, TVCA, and HCCA often perform better than individual dynamic models. Of the dynamical models listed here, only HWRF and the 2 Navy models, NavGem and COAMPS, had larger than 190 nautical mile error at 120-hour lead time. The current figure shows the track forecast skill of several models relative to climatology. Essentially, this sort of says how much better a forecast model does than just using climatology as your best guess. Dashed lines, the last 3 here in the legend, represent consensus ensembles, and they typically perform quite well. On average, the European Center model is the best performing track forecast model. That's this light blue line here, EMXI. And the Navy global model, NavGem, here in the red, is, while it's better than climatology, substantially worse than all the other dynamical models. Track forecast errors have generally decreased over the past few years, especially at 4 to 5 day lead times. However, intensity forecast errors have not markedly improved. As seen in this chart, average intensity errors of dynamical and statistical models are comparable to one another. Compared to climatology, the European Center model is actually less skillful at many lead times, while consensus models perform the best. The black line is the official forecast verification. Still, the average error of the best consensus intensity forecast at 5 days was 20 knots. Similar themes are seen in model performance over the East Pacific. The European Center model and consensus ensembles performed quite well in 2019, while the Navy model in particular performed quite poorly. Consensus models have performed well in the East Pacific over the last 3 years as well. The CMC-I, represented by the yellow line in this figure, is the Canadian global model, and it also doesn't perform particularly well on average compared to other global models. For some reason, NHC was outperformed at intensity forecasting in 2019 by many models, especially at long lead times. In fact, the best performing model at 5 day lead time for intensity over the East Pacific was the D-SHIPS, a statistical model. In general, errors over the past 3 years have been similar to those over the Atlantic, and a little less skillful relative to climatology percentage-wise. However, the absolute error has been less over the Pacific than the Atlantic. We will discuss several resources in class for information you can use to help forecast. The first day in the lab will be challenging, but as the quarter progresses, you'll become more comfortable with the tools at your disposal. We'll use a combination of in-situ aircraft data, satellite base intensity estimates, model forecasts, other remote sensing data, and more to make forecasts. These are some links to resources that you might find useful in real time. Have a look through them and see what you can figure out with a little research. We'll collectively explore many of these resources during our forecasting lab periods.